Hey everyone, this is Dr. Walker again. This is video 208. We're going to be talking about the electric field. This is going to be a very major topic, and hopefully I can get you interested in it by asking you this question here. How is this possible? So lightning, I mean, that's a big topic, but lightning, when you see lightning, what you're seeing is the flow of the charges through the air. So how is it possible that the charges can flow through the air when the air is supposed to be a pretty good insulator, but yet these charges can flow? So just think about it, post your thoughts in the comments below, and hopefully we can have a fun conversation. So the answer is definitely going to have to do with electric field. So let's talk about the concept here. We just talked about fields in the previous lecture, and we said that masses produce gravitational fields. Well, charges produce electric fields. So we can just draw an invisible field around this charge. So this is the electric field produced by charge Q. And we can call Q the source. So that's the one that is producing the field. And then what we're doing is we're going to put this test charge, which is denoted by little q, inside this electric field that was produced by big Q. Once you put this test charge in here, it's going to experience a force. And we just call it a test charge because the purpose of the test charge is always to experience the effect of anything. So in this case, the test charge is going to experience the effect of this electric field, and the effect is that it's going to experience a force F. So that's the concept of electric field. All charges produce electric fields. You place another charge within that field, that other charge will experience a force. Let's go ahead and take a look at two questions to see how well we understand this concept. First question. Does an electric field exist at a point P if there is no test charge there? It kind of sounds like the question, does a tree make a sound, right? If it falls in the forest, nobody's there to hear it, does it make a sound? It sounds kind of like the same thing. So pause the video, think about your answer, and the answer is yes. Okay, all charges produce electric fields. It doesn't matter if there's a test charge there. The test charge is just there to experience the effect. So if there's no test charge, then there's no charge experiencing a force, which is the effect, but there is still the electric field that is produced by that charge. Alright, you don't have to have a little test charge, little q, to experience that field. So, sorry, the field is right here. So you can just have a point here. You don't have to have a charge there. If you do have a charge here at point P, then that charge will experience a force. If you don't have a charge here, then you still have a field there. So let's keep talking about electric field. Let's introduce a definition now that we have learned the concept. So how do you find the electric field produced by a charge? So the electric field is going to be given by F over Q. So F is the force that the test charge would experience when placed within that field. And Q is the magnitude of that test charge. So basically what we're saying is that the electric field produced by this charge is going to be related to the amount of force that is experienced by a test charge placed in that field. So if this big charge Q produces a very strong field, again, I'm just drawing this just so that you can really remember that there's an electric field produced here. If this charge Q produces a very strong electric field that we use the letter E for, then that means that the test charge would experience a strong force. So you can see that they're directly related. However, the electric field produced by our big charge Q here does not depend on the test charge. Remember, we said the test charge doesn't even have to be there for there to be a field. So we divide the force by the magnitude of the test charge, because the electric field produced by big Q does not depend on little q. If we go back and think about F, which is the force between two charges given by Coulomb's law, if we think about the force between these two charges, it's given by K, big Q, little q, over r squared. That's the force between those two charges. So now if we say that the electric field produced by big Q is defined as this force divided by little q, then you can see that little q is canceling out, and we're left with K, big Q, over r squared. So this shows us that the electric field produced by big Q just depends on big Q and depends on how far away you are from big Q, but it does not depend on little q. However, if you want to know how much force that the test charge experiences, then that is going to be related to the electric field, and if you wanted to find that force, then you could just do F equals E times Q, for example. So the force experienced by the test charge is definitely going to depend on the test charge. That makes sense. If your test charge had a whole bunch of charge, well, those two charges are repelled more by each other, and there's more force. So the force depends on the test charge, but the field only depends on the source, which is big Q. So let's take a look at one more question that is going to allow us to use this definition of electric field. But before we do, let's just look at the units here. The units for electric field is Newton per Coulomb. That comes from newtons for force and coulombs for charge. And the electric field is a vector, so it does have a direction. We'll be talking about that in the next video. For now, I just want to focus on the definition. This equation here, and it has an absolute value of the charge, it's just giving us the magnitude of the electric field, how much electric field is there, and we'll worry about the direction later. So let's look at this last question here. For which case is the electric field at the black dot the greatest? So case 1 or case 2. So let's look at what is happening before you can pause the video. Here we have a charge Q, and the points where we're looking for the field created by this charge, this point is a distance r away. So in this case, this is the source, right? This is the charge that is producing the field at this point. So it's okay if we change notation. If a problem uses little q instead of big Q, you have to realize that this is the source producing the field at this point. For number 2, we have twice the charge producing some electric field, but the distance is also twice as far. So where is the electric field greater? For case 1 or case 2? So pause the video, think about it. Hopefully you use the equation for electric field, which is E equals KQ over R squared. But let's use little q this time because this example uses little q. So KQ over R squared would be the field produced at point 1 here. For case 2, however, let's see what has changed. The charge has become 2q instead of q. The distance has become 2r, so we have to have 2r squared instead of just the regular r squared. Let's go ahead and simplify and see what happens. K, 2q over both the 2 and the r get squared, so 4r squared. We've got 2 over 4, which is 1/2. We can bring that to the front. 1/2 times kq over r squared. So all we did is we plugged in the values for r and q that we knew, and we saw what happened. For case 2, we have half of the field that we had for case 1. So the greater field is going to be for case 1. So hopefully this makes sense. Just plug in what you're given and to see where you have a stronger field. And I will see you for the next video.